Welcome to the course Introduction to Uncertainty Analysis and Experimentation. In this lecture, we will look at examples of uncertainty calculations and we look at uncertainty in a result. So, there are some special forms of the result formula, that is what we will look at today, and also look at some issues that come up that could lead to possible errors. The first example is on non-multiplicative result relation. So far what we have done is we have seen multiplicative relation as a function which has only parameters raised to various exponents. And some constants there. So, this is the result formula. So, this form of the result was the multiplicative relation. There is no addition or subtraction in this. Now, what happens if the formula has addition or subtraction? So, that is what we will look at. The example taken here is temperature rise when a fluid flows through a tube which is being heated or say which is being cooled, does not matter. So, here is the statement: a fluid is flowing through a tube which is externally heated. The engineer has measured the inlet and outlet temperatures which were 63.2 degrees Celsius and 37.5 degrees Celsius respectively. The uncertainty in each temperature measurement is plus minus 3 degrees Celsius, and the person says, I want to know the uncertainty in the temperature difference. So, let us phrase the problem in our own terms and symbols. First, we have our result formula. We say that delta T is equal to the difference of two temperatures T 1 and T 2, and we say there are two parameters I and I equal to 2. Inlet temperature, which is parameter number 1, is T 1, and its mean value which is given to us is 63.2 degrees Celsius, this one. The outlet temperature is the second parameter T 2, and its value given to us, the mean value here is 37.5 degrees Celsius. Then we are also told the uncertainty in the measurements. So, in the inlet temperature measurement, the uncertainty is 3 degrees C, which is the expanded uncertainty. So, this is U, capital U T 1 bar, which is 3 degrees C, and the outlet temperature the same thing, U T 2 bar is 3 degrees C. Our result relation is delta T equal to T 1 minus T 2. This is not a multiplicative relation. So, the shortcut that we learned for multiplicative relations cannot be applied here, and we have to do the full analysis from first principles. So, first we calculate the mean value of the result delta T bar, which is the difference of these two temperatures T 1 bar minus T 2 bar, and this is 25.7 degrees Celsius. The result uncertainty relation is that U r bar square is the sum of theta I U x I bar all square added over for all the parameters, which in our case becomes U delta T bar is theta T 1 U T 1 bar, theta T 2 U T 2 bar, both of them are squared. Now, we were given U as the uncertainty U T 1 bar, and this technically is what we have been using the symbol T 195. So, this will be that constant factor which is for 95% it is 2 multiplied by the standard uncertainty in the measurement U T 1 bar. And when you do that, we get the standard uncertainty or we can call it standard combined uncertainty in each temperature measurement is 1.5 degrees Celsius. Now, we calculate the sensitivity coefficients. Now, theta I is defined as del r upon del x I, or theta x I if you want to call it. So, theta T 1 is del T bar by del T 1, this is 1, theta T2 is delta T by dt2, which is minus 1. So, in our uncertainty expression here, we have all the values of all these 4 terms. We substitute those and we get the sum of squares as 4.5, and so u delta T bar is equal to 2.12 degrees Celsius, which at 95% confidence level we multiply it by 2 to get the uncertainty as 4.24 degrees Celsius, and u hat delta T, which is the percentage uncertainty, is 4.24 divided by our mean value, which was the mean value of temperature difference. This turns out to be 16.5%. So, that is the way to handle additive and subtractive relations. If we thought that we could do it by saying that u hat r bar is the exponent of each into u hat of that expression, which we could do for multiplicative relations, where a I is the exponent of x I, then if we use this formula with our expression delta T equal to T1 minus T2, you will find that the result is completely off. This cannot be used for additive relations. So, that is the uniqueness of this problem, and difference between two values we come across very frequently in applications. We will now look at an example where we have to use the Taylor series method, the method number 2, which gives details about the breakups of elemental and random uncertainties. So, here is the problem statement. A circular plate is aligned normal to airflow in a wind tunnel. The instruments used were a drag force with a load cell. Velocity was measured with temperature. Velocity and temperature were measured with a combination bulb anemometer. So, this is an instrument which has a sensor which gives both velocity and temperature, and the diameter was measured with a vernier calipers. The random and systematic uncertainties are given in the tables in the information below. We have to calculate the drag coefficient and Reynolds number and their uncertainties. So, here we have 4 parameters. Diameter, velocity, temperature and force. Their nominal values that are given in this problem, they are like this. Diameter 0.5 meters, velocity 6 meter per second, temperature 30 degrees Celsius and force 4.7 newtons. And the random standard uncertainties. So, S means these are the random standard uncertainties. They are 0.1 millimeter in diameter, 0.25 meter per second in velocity, 0.1 degree Celsius in temperature and 0.2 newtons in the force. So, this sketch of this setup would look something like this, that we make a channel. These are 2 walls which are on the top and bottom. There is airflow established in there, and what we have here is a circular disc which is fixed to a load cell, which is anchored to the floor of the wind tunnel. So, air flows around this. Exerts a force which is measured by the pressure transducer, the force transducer here, the load cell. The velocity is measured by putting an instrument, and what we do is we have this instrument which has been put here. It has a sensor, and this gives both velocity of the air. So, this is air going in and temperature. So, we have these two measurements. The diameter of this disc we have measured separately as d. The load cell force is measures the force. So, the way we will calculate the drag coefficient, the definition of drag coefficient is force divided by half rho v square times the projected area normal to the flow, which in our case is the force divided by, this is pi d square by 4. So, this will become 8 f rho v square d square. Now, when you see this problem, we got rho here, and if you look at the other result formula, Reynolds number, this is rho v d divided by mu. Rho and mu have not been measured, but we have measured the temperature, and that is the basis on which we will get rho as a function of temperature, mu as a function of temperature, and then we can go ahead with this calculation. So, let us see how to solve this problem. So, first we have our result formula for drag coefficient, and the nominal value is that we just put a bar. So, these were all the values which were measured. So, if you look at what we had just now in the previous slide, we had this value, we had this value, we had this value, and we have this value. This value is not directly available, but as a temperature. So, we first need to do a small calculation to get the temperature, and then from there the density. So, temperature, we have the nominal value of temperature, we need to get the standard uncertainty in the temperature. Using that information, we will calculate standard uncertainty in the density and also the density itself. So, there is a slight deviation, and our strategy for solving has to become slightly different, that I first need to calculate this, and for that purpose what we will do first is to calculate and tabulate all the random uncertainties and the systematic uncertainties for each measurement. So, there will be 4 such tables coming up. This is the first one where we are measuring, this is about the disc diameter d. We are given that the random standard uncertainty is this much. So, we have that value. For the elemental systematic uncertainty, we look up what instrument was there, and this was a vernier calipers. And from information from the web about different manufacturers and what they have reported and what their instruments do, here are some typical values, that the vernier accuracy is plus minus 0.5 millimeters, and the symbol for that is BD1. This is an elemental systematic uncertainty, and this is 0.25, which is half of this value, because we are going to take these values at 95% confidence level. Then vernier resolution is 0.01 millimeter, which we take as it is, and vernier repeatability is 0.01 millimeters, that also we take as it is. And then we go back to the formula here. This is the systematic standard uncertainty in diameter. These are the elemental systematic standard uncertainties. 3 error sources were there, k is 1, 2, 3 here, 1, 2 and 3. We put them, and this is what we get. So, that is our B d bar. So, that takes care of the diameter. Now, let us go to the next parameter, and here we are looking at air velocity v. From the information that is given to us, the random standard uncertainty in velocity is 0.25 meters per second. We now have to estimate the BV bar, which is the systematic standard uncertainty in velocity from the elemental standard uncertainties. So, again we can go to the web, look up what all instruments are there and see what the manufacturers tell us. And from there we are able to identify two sources of systematic error. One is anemometer accuracy, which in one case is specified as 0.3 meters per second plus 5% of measured value. So, measured value is nothing but what we have been given, that is 6 meters per second. So, measured value is 6 meters per second, multiply that by 0.05, add 0.3 to it and that is the value we get. So, this is the accuracy and divide this by 2, we get 0.28. Again we are operating at 95% confidence level. So, this is BV1 bar. Then anemometer resolution is 0.01 meters per second. So, BV2 bar is 0.01. So, we put these values over there and our systematic standard uncertainty in velocity BV bar is 0.28 meters per second. So, we got both random and systematic standard uncertainties for velocity. We next look at air temperature, and remember this is something we want to calculate density and viscosity. We are given that the random standard uncertainty there is 0.1 degrees Celsius. We need to get the systematic standard uncertainty. So, again we do the same thing, look at what instruments tell us, and we have instrument accuracy is 0.05 degrees Celsius and at 95% confidence level this becomes 0.25, half of that. So, the elemental systematic standard uncertainty due to accuracy is 0.25 and similarly because of instrument resolution which we take as 0.1 degrees C. So, the units here are degrees Celsius, this is 0.1 and we go back and add it in this formula and we get that the systematic standard uncertainty in temperature is 0.27 degrees Celsius. And then the fourth measurement is the force. We are given that this random standard uncertainty in the force is 0.2 newtons. We look up, so this is the force, a similar table, and we are able to identify 4 sources of elemental systematic uncertainties, which is non-repeatability 0.1% of full scale. Full scale we have taken as 6 newtons and we are measuring about 4 point something newtons. If we had another instrument which was of 10 newtons range, this would have been 10. So, at 6 newtons, which is the closest that it captures 4.7 newtons, we get this is 0.06 and at 95% confidence level this becomes half of this. So, the elemental systematic standard uncertainty in force is due to accuracy non-repeatability is 0.03 newtons. Then there is hysteresis associated with the load cell, which is quoted as 0.03% of full scale. So, if we take that multiplied by 6 and we take that as 0.018 newtons. Then there is non-linearity, and error due to that is 0.03% of full scale. So, Bf bar F3 bar is 0.018, which is this into 6 newtons. And the fourth one is due to creep, which is 0.02% of full scale, and this we get as 0.012 newtons. So, this is Bf bar 4. So, we put all these values in this relation and our value is 0.041 newtons, that is the systematic standard uncertainty in the force measurement due to the load cell. So, in doing this we did for all 4 measurements we got the systematic standard uncertainty and the random standard uncertainty. Now, we will go back to doing the calculations for density. So, the first thing is we look at what is uncertainty in the temperature. The mean value of temperature is 30 degrees Celsius, and from standard property data we get the mean value of density at this temperature as this, we are assuming this is at 1 atmosphere. We are given S T bar as 0.1 degrees C. From the table, we got B T bar as 0.27 degrees Celsius, and we calculate the standard uncertainty in temperature at the sum of the square of these two, S T bar square plus B T bar square under root. When we do that, this is the value we get. U T bar is 0.29 degrees Celsius. So, now we can proceed in two ways, either use the result formula for an ideal gas or we use the tables data, and what I have done here is to use data from property tables, where it is listed temperature and density at 1 atmospheric pressure. So, there is a temperature, there is a density. So, these are the columns which are there, and these are discrete columns, maybe at 5 degrees Celsius interval or 10 degrees Celsius, and from there I have taken data. So, our temperature is 30 degrees Celsius. So, say well this is 30 degrees Celsius, and the next few entries are there, and we taken that we will take one lower temperature which is at 10 degrees below this 20 degrees Celsius, and another 10 degrees above this which is 40 degrees Celsius, and then we read out the corresponding values over there. So, there we have d rho by dt, we approximate this as delta rho by delta t. So, this is a numerical technique of calculating the sensitivity coefficient. This is at 40 degrees Celsius, it is 1.127. So, this is the value we got at 40 degrees Celsius minus 1.204, this is at 20 degrees Celsius, this is 40 minus 20, and we get d rho by dt as minus 0.00385 kg per meter cube per degree Celsius. And then, being a single parameter property, the result formula gives that u rho bar is this value, which is the sensitivity coefficient, multiplied by u t bar, which is this value here, and the answer is 0.00112 kg per meter cube, and the expanded uncertainty is double this value at 95% confidence level. For the drag coefficient calculation, we do not require the viscosity part, but I followed the same process that we looked at another table, where instead of rho it gave the value of mu, again like that, and we picked up the value at 20 degrees C and 40 degrees C. So, this is dynamic viscosity at 40 degrees Celsius, and this is dynamic viscosity at 20 degrees Celsius, 40 minus 20, and this is the answer we get, the 0.00465 into 10 to the power minus 5 kg per meter second per degree Celsius. And again, so u mu bar, we multiply that by u t bar, which is this much. So, if you have to do the Reynolds number calculation, then we will require both these properties. One is the mean value and the second is the standard uncertainty. These two values we carry forward. For now, we are only looking at density. So, this is what we need. We have the nominal density as this value here and the uncertainty as this value over here. So, now we can go back and say, now I have all the information to calculate the nominal value of the drag coefficient, and we will do that calculation at the mean values that are reported. So, this is f bar upon rho bar v bar square a bar, or 8 pi rho bar v square bar d square bar, and we substitute all the numbers that we had earlier. Our drag force, which is given to us in the problem statement, was 4.7 newtons. Density we just calculated. The velocity is 6 meter per second. So, this is this is not 6, this is square into 0.5 square meters, this is the diameter. So, when you do that calculation, we get 1.143. So, the nominal value of drag coefficient is 1.143. Now, we have to calculate the uncertainties, that is our next thing. And for uncertainty calculation, we have two options. One is, we know that by looking at this relation, this is a multiplicative relation. So, we can take the shortcut, or we can go the long way to get all the sensitivity coefficients. but because we are fully following TSM method number 2, we will take the long method. It gives us lot more information which the simple multiplier formula does not give. So, this is what we have, and we will ultimately we are working with the fact that u CD bar square, this is equal to theta d u d bar square plus theta v u v bar square plus theta rho u rho bar square plus theta f u f bar square. So, that is the formula that we will ultimately use, but before that what we need to do is we need to calculate all these sensitivity coefficients, and that is what we have done here. We start with theta d, d C d by d d, we differentiate it, we put all the values at the nominal values. So, theta d bar, which is the nominal value of the sensitivity coefficient, is this much. Similarly, theta v, we differentiate with respect to v and we get this relation, and that gives us minus 0.3809 seconds per meter square. Then sensitivity coefficient for density, this is 8 f upon pi rho square v square d square with a minus sign, and that is what we get. And finally, sensitivity coefficient for the force, and we get this formula, substitute the numbers into each one of these, and this is the number we get, and the units of each one of them are written here. This is per meter, this is seconds per meter, this is meter cube per kg, this is per Newton. So, thetas are all dimensional, but their dimensions are not the same as the result or the measurand. This is something different. So, thetas are calculated now. Now, we can go to the next step and let us start listing all these in a table. So, in this table we will first make the first 7 rows, which is just taking data from what we already have and putting it over here. So, this is variable number 1, which we will see is diameter, number 2 is the velocity, number 3 is the density, and number 4 is the force. So, that is what here in the first row, symbol of the variable dv rho f, then description, this is disk diameter, this is air velocity, air density, and this is drag force. And the units for these parameters, meters, meter per second, meter cube per kg, and newtons. So, we are going to be sticking, is best that we always stick with SI system, and even though we use other numbers come in, millimeters come in, kilopascal, megapascal will come, ultimately we will write everything in, all calculations in SI. The nominal value we have been given, so xi bar is 0.5 meters here, 6, 1.164 we got from our earlier calculation. So, this is not in that sense a measured value, but from temperature we got this value, and this is 4.7 newtons. Now, we list what we have already got. Random standard uncertainty of the measurement has been given to us. We have just put it down here in the same units. This is 0.0001 meters, 0.25 meter per second. We do not have this value for density. If we wanted, we could have calculated that, but we did not, we did not do that one. So, we skipped this part, and this is 0.2. So, this is all given to us. Then we write the systematic standard uncertainty of the measurement Bxi bar. This is this much is been be calculated. This we just calculated as 0.28 meter per second. We just reproduce it here. This we have not calculated, and this is coming here 0.041. In a minute, we will see that even if we did not calculate these in the ultimate analysis, this does not matter, because contribution of density to the uncertainty is quite negligible, and we would have been quite happy to say that density is constant and we go ahead with it. We could have solved the problem that way also. So, the combined standard uncertainty of the measurement Uxi bar, this is square root of the sum of the squares of these two. So, this is square root Sxi bar square plus b x I bar square whole square root. So, when you do that, this square plus this square root, you get this value. Similarly, here this one and then this one. So, all of these have units of the measure and so rows 1 to 7 we have got whatever we wanted there. Now, we have already calculated the sensitivity coefficient. So, we will start writing that down here. So, this is theta bar d, this is theta bar v, this is theta bar rho and this is theta bar f. So, same values that we just calculated in the previous slide, we have just put it here. Now, we start combining and say random standard uncertainty contribution of the measurement theta I bar into S x I bar whole squared. So, this row 9 is theta I bar, which is row number 8, multiplied by S x I bar, which is row number 5. So, this is what we got and we squared this. So, this into this squared comes here. Similarly, we are doing for every one of them and get these numbers. We did not have these two values. So, again here this value is not there. Next, systematic standard uncertainty contribution of the measurement. We can get theta I bar b x I bar there, and we do this time instead of row number 8 and 5, we do the product of 8 and 6, square this, and these are the numbers we get here. These are, so this is again like before, not there. And finally, combined standard uncertainty contribution, which is theta bar into u x I bar whole thing square. So, here we are multiplying row 8 multiplied by row 7 and taking a square and listing the numbers over there. So, this is one part of the table is done. We can continue now and do the remaining part of this table. We add up all the values in one by one in these rows, these 3 rows 9, 10 and 11. So, this is adding all the elements in row 9, we get and square root of this. So, these already we have put in each table, we just have to add them up and take the square root, and this is the answer we get here. This is coming from row 10, we added all the numbers in that row and took their square root, that is what you get here. And the combined standard uncertainty of the result, again we do the same thing, we go back, we have those elemental values listed in row number 11. So, here is 11, this one, and take a square root and this is 0.1513. So, this is what we were looking for, standard uncertainty in the drag coefficient. This is 0.1513, and of course, all of these have the same units as the drag, which will be newtons. Then we calculate the expanded uncertainty of the result, which is u r bar C L, and we will take it at 95% confidence level. So, this K C L is 2 and we multiply this by 2 and we get this value, this so many, sorry, this is drag coefficient. So, this is got no units. So, these are the two things we got. Then we look at the individual contributions. So, what we will do is we take the 3 rows there 8, 9, 10 and 11 and normalize them on the value of this, which is your u r bar square, the result. So, we will normalize it on the square of this. So, this raised to the power 2. So, this is 9 row divided by the square of this, and these are the numbers that are listed over there when you do that calculation. This is row 10 divided by the square of this, which will be this, and this is row 11 divided by this squared, which is these values. So, having done all of that, we can then pick up this number and express our result. We say that the drag coefficient was the nominal value 1.14 and what we got as u C d bar, this is 0.31, this was C d bar, or as a percentage it is this. So, this is u hat C d bar and this is C d bar. Being drag coefficient, there are no units here, it is dimensionless. And this relative value came from here, where 0.13 divided by 1.14, which is about 27%. So, as far as the what is the answer was there, this gives us the full information. This is our answer. But the point of doing method 2, which is what we are looking at here, the Taylor series method 2, is that we got lot more information here in this table. So, let us see what it is telling us. First, let us look at the last row, contribution to standard uncertainty of the result. So, here is what we have. This value, this and this. They will all add up to 1. But you look at their magnitudes, this is something into 10 to the power minus 5, this is 5 point something into 10 to the power minus 6, this is 0.89, 0.106. So, both of these are like at least 4 to 5 orders of magnitude smaller than these two terms. And this means that the diameter, this is what is for that, and this is density. The density uncertainty came because of uncertainty in the temperature, and it is telling us that uncertainties in these two parameters have almost no contribution to the drag coefficient. So, we could be quite justifiably neglect it, the answer will not be very much different. Now, the other two numbers, that is what we are looking over here, this one and this one, they are still, of course, both of them are much bigger than the other two, but amongst them this is about 9 times bigger than this one, 0.893, 0.106. So, what it tells us that the single biggest contributor to uncertainty in the drag coefficient is coming from the velocity measurement. So, a strategy to reduce uncertainty in the drag coefficient should begin by tackling the velocity measurement and then further look up into the contributing elements, and what we see is here the random uncertainty in the velocity measurement is 0.396 and the systematic one is 0.4967. So, about 40% is coming from here and 50% is coming from there roughly. So, what do we see? Both of them are equally important. So, to reduce this, we got to tackle both of these. So, here we have to get a better instrument. Here we decide to see if there is anything else happening in the experiment, take much more readings and reduce the uncertainty as much as possible. And now, within this also we see that in this row, the random uncertainty contribution, this is the biggest one, then the force. And similarly here, again this is very small, this is also small, and among the systematic uncertainties, the biggest contributor is in velocity measurement. This information you can also show graphically in a Pareto chart, and in one picture you get to know what is doing what. So, that is a lot of information that came out because we have Taylor series method 2, Taylor series method 1 would not have given us this much detail. We also have another option. If we look at the drag coefficient formula, this is 8f by pi rho v square d square. This is a multiplicative relation. There is no addition, no subtraction. So, we could have taken a shortcut, and the shortcut goes like this, that u hat, which is the relative standard uncertainty in the drag coefficient, the square of that is A f into u hat A f. This is relative standard uncertainty in force. A f is the exponent of force. In this case, exponent of f, which as you can see from this relation, it is 8 f. So, A f is equal to 1. And similarly, we add 3 more terms, one for density, one for velocity, one for diameter, and in this case we can see A f is equal to minus 1. In this case, A v is equal to minus 2 and A d is equal to minus 2. So, something nice comes out quite quickly here is that because of these 2's, these uncertainties will get magnified more than the ones where the exponent is 1. That is one thing comes out. The other thing, if you had compared, when we do the calculations for u hats for all these 4 values, we will find that u hat d is very small, whereas u hat v is not that small. And we will immediately see why uncertainty in velocity is having such a big impact, because firstly its value is reasonably large, and second its exponent is 2. So, in this formula when you square it, this will become 4 and then you take the square root. So, the contribution coming from velocity is getting further amplified, and that is what we saw in the earlier analysis. So, we could have quite comfortably done this method. Remember the definition of u hat, say u hat in any one of these parameters, let us say force, this is u f bar upon f bar, the nominal value of the force. So, it is the same relation for all these relative standard uncertainties, and we could have done it because the formula happens to be a multiplicative relation. So, that completes our discussion on the drag coefficient. In this experiment, we will calculate one more result. So, this is an experiment where there are 2 results, and here the result Reynolds number is rho V d upon nu. Rho and nu we just saw, they came from temperature, and we had calculated their uncertainties. In addition, we have V and d. In this case, the force is not a parameter in this formula. So, there are 4 parameters in this result formula. You can follow the same procedure that we have done there. In fact, 3 of the columns will be common, only mu is the new one coming in, and you will see that rho and mu are both very small contributors, but diameter is also a relatively small contributor. The dominant thing is coming from V. However, V has an exponent of 1 when we look at it as a multiplicative relation. So, this is the multiplicative relation. So, we can apply this, that the relative standard uncertainty in Reynolds number is related to these 4 terms, where all these coefficients or the exponents, they are 1. So, I will leave this as an exercise for you to do, and with that we conclude this example. Now, we look at another case of a multivariate relation, but we see how we could go off in the procedure and do something which is very wrong. So, the example here is as follows. This is an example of a CNG cylinder which you see in many vehicles. So, it says a high pressure cylinder contains methane gas at 60 bar and 27 degrees Celsius. The internal volume of the cylinder is 65 liters. Uncertainties are in pressure plus minus 2 bar, in temperature plus minus 2 degrees C, and in capacity plus minus 0.2 liters. What is the mass of methane in the cylinder and its uncertainty? So, this is question number 1. And then there is a second question. If the uncertainty in mass is to be less than plus minus 3%, then what should be the uncertainty in pressure measurement with the other two uncertainties remaining the same? So, we are just doing a calculation here. We are not saying how we are going to reduce that uncertainty or in the measurement, but it just tells us that if we want, this is our criteria, what do we expect? So, here is how we will do this. So, this is methane in a cylinder, and we have been given that the mean pressure is 60 bar and its uncertainty U P bar is given as plus minus 2 bar. Then we are given that T bar, the temperature is 27 degrees Celsius, which is 300.15 Kelvin, and U T bar is equal to 2 degrees Celsius. Then we have volume of the cylinder. Mean volume is given as 65 liters, which is 0.065 meter cube, and uncertainty in the volume, this is given as 0.2 liters, which is 0.002 cubic meters. So, this is all the information we have, and we are asked what is the mean value of the mass and what is the expanded uncertainty in the mass. So, we first we recognize that we have 3 variables. We can call this x1, this is our x2, this is our x3. So, 3 parameter. The result formula has 3 parameters. And what is the result formula? That we assume that this is an ideal gas behavior, and so we have PV is equal to MRT and M is equal to PV upon RT. So, to calculate the mean value of the mass, we just say this is equal to, we substitute these numbers there. R for methane we guessed from the tables as 0.5182 kilojoules per kg Kelvin, or we will use with SI units consistently, we will use joules per kg Kelvin. And of course, for pressure this will become 6 into 10 to the power 6 Pascal. This is 2 into 10 to the power 5 Pascal. So, we put all these things here in mass, which is 60 into 10 to the power 5 Pascal multiplied by 0.065 cubic meters, 518.2 joules per kg Kelvin multiplied by 300.15 Kelvin, and when you do all of this, we get the answer as 2.507 kg. We can even round this off and say this is 2.5 2.51 kg or just 2.5, that we will see. So, that is half the story done. Now, for the uncertainty calculation, we will calculate, we have two options. One, we go the long way, calculate the sensitivity coefficients, or we take a shortcut knowing that this is a multiplicative relation. So, we will do it both ways. In the first case, the full way, our relation will become u m bar square is equal to theta p into u p bar square plus theta v into u v bar square plus the same thing for temperature. We need to calculate three sensitivity coefficients. So, we do that. Theta p is equal to d m by d p, and this is v upon r t, and when you do this whole calculation by substituting that the mean value of p, this will be v bar upon r t bar, this is 4.179 into 10 to the power minus 7, and the units are there, kg per Pascal. So, thetas have units generally, they need not be the same, thus they may not be the same at all. Now, theta v is d m by d v, this becomes p upon r t, and you do this whole calculation at the mean values, theta bar v bar, this is equal to p bar upon r t bar, and this is 38.576 kilograms per meter cube. And similarly, the third one, d m by d t, this is minus p v upon r t square. So, we get, we substitute all these values into that at the mean point, minus p bar v bar upon r t bar square, put the values and you get 8.354 into 10 to the power minus 3 kg per Kelvin. So, there we are, we got all our sensitivity coefficients. Now, we need the standard uncertainty in each. So, we realize that the standard uncertainty in a variable will be expanded uncertainty in that variable divided by the KCL. We assume that it is uncertainty is reported at 95% confidence level. So, KCL is equal to 2. So, what we get here is that u p bar is equal to 1 bar, which is equal to 10 to the power 5 Pascal. U v bar, this will be 0.0001 meter cube, half the value of the uncertainty quoted, and u t bar is 1 degree Celsius. Now, you put all these values in this, we have all the thetas which is given here. So, these are the values that goes with this value goes with this value goes with this. Now, you can even say this is 1 Kelvin. We put it in this relation, do the whole calculation, and the final answer is that u m square is 0.00183107. I just kept so many decimals, we will round it off in a minute, and with that we get u m bar as 0.04279 and u m bar 95% confidence level. This is twice this value, which will be 0.08358 kg. This is also kg. Now, we can round this off and we say this is 0.083 kg, nothing more is really Okay. We could even have said 0.084. So, that is what we wanted. One part we could have calculated the relative uncertainty u hat m bar. This is u m bar at 95 divided by the mean value of the mass, and when you substitute the values and calculate it, this comes out to be 3.33%. So, we did the long method, got the answer that we were looking for. This is the answer for the first part. We got the mass earlier. This is the, so the result answer becomes, it is 2.51 kg plus minus 3.3% at 95% confidence level. That is our answer. Now, let us look at the other method, the shortcut method we can say. We recognize that the result is a multiplicative formula. So, if you look at m, is P v by R t, then we write the exponents. So, P, V and T are the 3 parameters. The exponent of P, A P is 1, the exponent of V is 1, exponent of T is minus 1. So, then we know that for such a relation you can take a shortcut and say that u hat or maybe capital U hat, which is a non-dimensional standard uncertainty, this is the sum of the individual coefficients multiplied by their relative uncertainties. Where u hat for any parameter is defined as u divided by x I bar. So, now we need to calculate these values. So, that we can do that u hat p bar, this is u p bar upon p bar, and when you do the calculation, this comes out to be 0.01667. U v bar hat, this is u v bar upon v bar, and when you do that calculation, this will come out to be 0.001539, and similarly u hat t bar, this is equal to u t bar upon t bar, and this is 0.003332. I have just kept decimals just because they come to show you that somewhere on the line we have to do the round offs. Now that we have this, we can substitute these values in the. So, we have the u hats bar which is coming here, and we have the A p which are coming from here. We just substitute all of that, and when you do the calculation, we get u hat m bar, this comes out to be 0.017, and using this formula here, this one, we get u m bar is 0.017 into the mean value of the mass which we calculated earlier as 2.5074. This comes out to be 0.03767 kg. This has got no units. U hat is non-dimensional. You can look at this. So, this is that, and finally u m bar, this is the double the value of this, which is 0.07534, and when you calculate the relative uncertainty, this is 3%. Earlier we got 3.3%, now we are getting 3%, and all of this is because of the various round offs that we have done on the way. So, if we had kept more decimals over here, more significant places, we would have got a slightly different answer. So, that is another feature of uncertainty analysis, that we are doing so many calculations, often involving very small numbers or very big numbers. So, if you round off in between, it could lead to an error. So, this is the second method. So, we did the calculation by the multiplicative formula, and what you can see here, this is much less effort, much less calculation than what was there in the first one. Of course, if you are doing it on a spreadsheet or you have a program written for it, any of them will be the same effort. Now, we come to the second question, that it says that u m bar has to be less than or equal to plus minus 3%. And the question is that temperature and volume uncertainties are same. What should be uncertainty in the pressure measurement? This is the question. So, we would be tempted to think that we can write, now I want to calculate P. So, P equal to MRT upon V. We look at this as a multiplicative formula. And when you do that, we can then write u hat P bar, which is what we want to calculate, as u hat m bar square plus u hat T bar square plus u hat V bar square. U m bar is given as plus minus 3%. So, we can get that standard error in mass. This is, we can calculate that ratio. So, this is 0.3%. So, u hat m bar, this is 0.015 multiplied divided by 2, the KCL factor. And so, this number comes here. We already have the other two numbers, and when you put all these things here, this comes out to be 2.3847 into 10 to the power minus 4, or u hat P, this is equal to 0.15 0.01544, and then you can calculate u p bar, this into the nominal value of the pressure, which is 60 bar. So, it is this multiplied by 60 bar, and this becomes 0.09265, or you can call it 27 bar. And so, u p bar is 0.185 bar. So, you may think we got the answer, but we have done a big mistake. We have used this relation. And in this, what we have done is that P is on the left side, but remember P is a measurand. And in uncertainty analysis, we have always written that the result is a function of the various measurands, or we have called these parameters or variables. So, the entire analysis rests on this logic. To recast the equation in this form distorts this basic requirement of the uncertainty analysis, and so this is wrong. So, this entire answer that we have done here is wrong. So, then what is the correct way to do it? We go back to our result formula, that measurements are on the right side. So, m is equal to P v upon R t, and we get the same relation earlier, that u hat m bar square is equal to u hat p bar square plus u hat v bar square plus u hat t bar square. And now we recast this, because we want the uncertainty in the pressure. We say u hat p bar square is equal to u hat m bar square minus the other two uncertainties. And then we put all our values that we had earlier and do this calculation. And this will give us the value of 0.01454, which means that u hat p bar is the square root of this, and then multiply this by 60 bar, and the answer you get. So, this is square root 0.01454, this value comes here, and this final value is 0.8726 bar. No, okay, there is some, this is not right. You take the square root of this will be about 0.2, roughly 0.2 something. Yeah. No, sorry. Okay, we go back. We do this entire calculation. And we do this calculation, and we get the answer here as 0.000211153. And we take the square root of that, and we get u hat p bar is equal to 0.01454, and from there we get u p bar as this value multiplied by 60 bar, which is equal to 0.8726 bar, and the expanded uncertainty in pressure should then be twice this value, which is about 1.75 bar. So, this is the right answer, and it tells you that earlier we were measuring the uncertainty of 2 bar. If we reduce it to 1.75 bar, we can reduce the uncertainty from 6% something to 3%. So, that is another example where you are required to calculate expected uncertainty in the measurement if you want to achieve a certain uncertainty in the result. So, that is how we have done this. We saw the entire process and we got the answer. So, we solved this problem. The next example is of multiple tests, repeated tests. So, here is the problem statement, that somebody got a sack full of agricultural waste, was sent to a laboratory for ascertaining its calorific value. The laboratory took samples from different parts of the sack and measured the calorific value following a standard test, IS 1350/2017. The following are the data of the nominal calorific value. So, we have got all these numbers which came out. Now, in this, there is no information about the instruments. We do not know what the elemental contributions, random or systematic uncertainties are. we assume the experiment has been conducted in the same way, and we also assume in this particular case that if we have a big bundle of some material, we take a sample from there, we take a sample from there, we take a sample from there, there could be variations from sample to sample. And that could be one of the objectives of such an experiment to begin with. But we are assuming that the sample does not vary, it is homogeneous. We cannot use the TSM techniques, and the data that is given, the appropriate approach is multiple tests, repeat tests. So, let us look at the analysis, and this we have done in a spreadsheet. You can do it in many other ways. So, here are in this column all these, this one, these are all the values that we have been given. This is the calorific value in kilojoules per kg. Using these values, we got that the sample size is 13. We calculated their average, which came out to be this, and we calculated the standard deviation of this sample, which came out to be this. Next, we applied Chauvinet's criteria. That should we reject any reading, and to do that we calculate the deviation of each reading, which is xi minus x bar upon s. So, xi is say this value, x bar is this value, s is this value, and we do this calculation for every value we have in this data set, and this is the deviations given here. Then we ask the question that if 13 samples are, that 13 is our sample size, what is the maximum permissible deviation according to this criteria? And we look up the tables and we say that it says that for sample size 10, you should have no deviation greater than 1.96. For 15, the deviation should not exceed 2.13. So, let us take a little more stringent criteria of 10, which is 1.96, and we look at all these numbers here, and we find that 2.25, its value exceeds 1.96, the modulus of this value. That means, mod di that we got should not exceed the di maximum given by this criteria, the Chauvinet's criteria. So, this reading we have to reject. So, we do that, take all the remaining readings into this column. Again, now our sample size is 12, mean, this is our standard deviation, and again we calculate the deviations for each measurement and we get these values, and again our limiting number is 1.96, none of these are more than 1.96. So, all are okay. Then we calculate our sample standard error, which is s by square root n, which is 825.87 divided by square root 12, which is this, and this has got the units kilojoules per kg. So, does the mean value and the standard deviation. So, that is our standard error, standard uncertainty. So, our now result becomes a mean value of the calorific value is this much, UCV, which is SCV, which was what we got here, 238.4, or you can write 239 also. At 95% confidence level, this is 2 times this value, which is 476, and the relative uncertainty is 476 by the mean value, or 2%. So, our report, calorific value is this much plus minus this much at 95% confidence level, or it is this much plus minus 2% at 95% confidence level. So, that is the simple way by which we can get the result uncertainty from multiple tests and repeated tests. With those examples, we will conclude, and we have seen some examples of calculating uncertainty in the result. We saw that there are different ways in which the problem can be posed, and in some cases it is a pre-test analysis and then there is the post-test analysis. With that, we conclude this lecture. Thank you.